Bismillahirrahmanirrahim, dear students, grade 11, and we are discussing chapter number 8, strong acids and strong bases, the strength of acids and bases. This lecture number will be 55. I will check chapter number 8, the strength of acids and bases, grade 11. So already I told you that strength of acids and bases depend upon how the acid is going to donate proton. If ability of acid is more to donate proton, this is called a strong acid as compared to the other acids. If the ability of the acid is going to be acid, accept electron, proton is a great, it's called a strong base as compared to other means. So this ability of the acids and bases depend upon the value of Ka. Ka is called ionization constant or dissociation constant for the acid, and Kb is a ionization constant and dissociation constant for the bases. So ionization constants or dissociation constant for the acids, and ionization constants and dissociation constants for the bases. So, dear students, there is here derivation for it. So I am going to derive here. So suppose you have this is the acid according to the Bronsted-Lowry concept. So this acid is going to be donate proton, Bronsted acid, Bronsted base to give the conjugate acid and conjugate base. You done this one. So this is the according to the Bronsted-Lowry constant for acid and bases. This is the equilibrium constant, concentration of hydronium ion, concentration of halide ion, concentration of hydrogen halide, concentration of water. So dear students, concentration of water is a constant because it is in the large axis. Water is as a solvent, so concentration is constant. So hydronium ion, halide ions divided by hydrogen halide. So this constant for the acid is equal to Ka, which is called ionization constant for the acids. So hydronium ion plus halide ions, there is a hydrogen halide. This is called Ka, ionization constants for the acids. So if the value of it is dependent on temperature, we must write with the temperature. If the value of Ka is greater, larger value of Ka is stronger the acid. Larger the value of Ka is stronger the acid. Strong acid will be more dissociated. Then there is another we more right preferred like this one, pKa minus log K. So if you see this table, yellow table, Ka value is a very large and pKa will be small. If the value of Ka is very large, the pK will be very small. The acid is highly dissociated. I am going to give some examples for you. At 25 degrees centigrade, perchloric acid has a Ka 1 into 10 raised to power 10, pK is minus 10. Inverse. Hydrobromic acid 1 into 10 minus 9, minus 9. So this is the vice versa for this one. There is here calculation. I am going to write this calculation, then you have to solve this one. This is the derivation for the ionization constant for the acid. Ionization constant for the acid. Ka. So numericals calculate the concentration of hydrogen ions. Calculate the concentration of hydrogen ions of solutions of 1 molar solution, and the value of Ka is 7.2 into 10 raised power minus 4. And acid is a weak acid, hydrogen fluoride. Hydrofluoric acid is a weak acid. It's a net dissociate. So write the equilibrium equations. Somehow it is going to be iodized, not whole, because it is a weak acid, just like this one. So this is the initial concentration. Initial concentration of hydrogen fluoride is 1 molar. Initial concentration of hydrogen 0 and fluoride is 0. Equilibrium concentration you done in the equilibrium chapter. So it is the maximum, minimum. When the chemical reaction goes forward a step, the concentration of hydrogen fluoride decreases and concentration of hydrogen fluoride are going to be increased. So this will be a hydrogen fluoride 1 minus X, and this will be a X, and this will be a X. So write the Ka equilibrium constant. K will be is equal to concentration of the hydrogen ions, concentration of the fluoride ions, concentration of hydrogen fluoride. Put the values. Ka is 7.2, 10 raised power minus 4, and hydrogen concentration you have here X. Fluoride is X, so X square divided by hydrogen fluoride, that is 1 minus X. So there is one thing you have to remember. Since X is very small as compared 1, this X is very small as compared 1, so the term denominator X side can be approximated. So you don't write this one, no need for writing this. Approximated. That's why 7.2 into 10 raised power minus 4 is equal to X square. Squaring both sides, then you will get hydrogen ion concentration 0.268, and this is the hydrogen ion concentration. Very simple numericals are also here. pH of the this is example number 7. This was example number 6. So please look here very carefully. Then I am going to start another one, numerical. A pH of 1 molar solution, pH is given, is 2.85 of 0.1 molar solution for the acid. Name of acid is not mentioned. And calculate the ionization constant of acid, means Ka you have to find. Find the value of Ka. You know that if we are going to calculate Ka, then we must have the value of the H, means hydrogen ion concentration. Hydrogen ion concentration you must have. So if you are going to convert the pH 2.85 into the hydrogen ion concentration, then taking anti-logarithm of minus 2.85, because pH is equal to minus log of hydrogen ion concentration. So you will get the hydrogen ion concentration by taking minus anti-log of 2.85. The answer will become, if you calculate, then hydrogen ion concentration will become 1.4 into 10 raised power minus 3n. After taking anti-logarithm of minus 2.85, you will get this answer. Now students, you have an acid, we have no name for this. This acid will give hydrogen ions in aqueous solution and conjugate base. We don't know what it is. It dissociates into hydrogen ions and conjugate base. So equilibrium concentration initial concentration is 1.4 into 10 raised power minus 3 means 0.0014, because you are going to change yes. If you change into decimal point, then 0.0014, yes. So this is the hydrogen ion concentration like this one. 0.0014. So initial concentration is 0.1 here. Initial concentration is 0.1, and here for the hydrogen ions and conjugate base is 0 because initial is 0 here. So when the equilibrium is going to be formed, students, you have the 0.0014 hydrogen ion concentration after establishing the equilibrium, so it should be subtract. So 0.1 minus 0.0014. So you will get this 0.0986, and this will be a 0.0014 and 0.0014 m molar, like this. 0.1 is the 0.1 initial concentration. I have written initial 0, when equilibrium is going to be formed, you have the equilibrium of the hydrogen concentration 0.0014. So I subtract because communication goes to forward direction. 0.0986 m is given here, and for the hydrogen this and for the conjugate base this one. Then according to the law of mass action, then value of Ka is concentration for the hydrogen ions, concentration for the conjugate base, and divided by concentration of acid. So value Ka can be calculated for the hydrogen ion concentration is 0.0014, conjugate base same, so square, divided by concentration of the acid is 0.0986. So after solving this, when you are going to solve, you will get 2.0 into 10 raised power minus 5. Solve it and you will get the hydrogen ion concentration. From hydrogen ion concentration, we will get the value of Ka. So this is the strong acids and weak acids. Then there is strong base and weak base. Same I told you. For the acid we use Ka, and for the base we use Kb. If the value of Kb the base which has more ability to accept proton is relatively stronger base as compared to other. High ability. The strength of the base is defined as ability to accept proton from the solvent, water. So sodium hydroxide is very strong base, sodium and hydroxide ions according to Arrhenius concept. So you have the hydroxyl ions and hydrogen ions equal strength, you will get water. This is called neutralization. So you've done this before. Now here for the derivation of the basis Kb, so this is the base and this is the water. So a strong base means the base which has a more ability to accept the proton. This proton is accepted by the base. So hydrogen is added, then positive charge is created here, and hydrogen is gone to make a OH. So this is a Bronsted base, and this this is called conjugate base, and this is called conjugate acid. This is a Bronsted base and Bronsted acid. This is the for the base here. So you want to calculate the K for the equilibrium constant, concentration of hydroxyl ions, concentration of base and concentration of water. Same concentration of water is going to be constant, same derivation. Then concentration of BH plus concentration of hydroxyl ions divided by concentration of base. Like this is a constant quantity, so we write Kb, concentration of BH, concentration of OH divided by concentration of B, like this one. This is called a Kb. Kb is called a ionization constant for the base. Kb value will be larger. Degree of ionization of base will be larger, the stronger the base. Kb will be the smaller, weaker the base. Yeah, pKb. So pKa and pKb. So pKb is equal to minus log of Kb. You can calculate by using this one. So pKb is defined as a negative logarithm of Kb. You can see this yellow table 8.3. The diethyl amine has a Kb 9.6 10 raised to power minus 4 and the pKb is equal to 3.02. So this is larger as compared to ammonia. If you compare this ammonia 1.7 10 raised to power minus 5 is less than that one, and pKb value is a higher 4.76. So diethylamine is a stronger base than the ammonia. So ammonia is a stronger base than pyridine. Pyridine is a stronger base than aniline. So there is a comparison given here, Kb and pKb values here. Now relationship between Ka and Kb. Relationship between Ka and Kb. Relationship between Ka and Kb. We know that Ka is a hydrogen ion concentration for the acids, and Kb is a hydroxyl ion concentration. Kb for the bases and Ka for the acids. So we have to means prove this. Ka multiplied by Kb is equal to Kw 1 into 10 to the power minus 14 at 25 degrees Celsius. So you have to prove this one. So this is the acid, acetic acid, going to dissociate small extent hydrogen ions, acetate ions. This is the conjugate base. So for the Ka concentration of hydrogen ions, already this is repeated. Hydrogen ions, acetate ions, and concentration of the acid. This is for the Ka. So when we are going to write for the conjugate base, so this is a conjugate base acetate in aqueous solution with water. So this water acts as a bronze state acid. So this is going to be formed acid Ha and the hydroxyl ions. So dear students, same this is a base. This is for the Kb. Concentration of the acid Ha, concentration of the OH divided by concentration of the A, because water is going to be constant here. So if you don't write for the water, so it is going to be constant directly because Kb and water constants, write only concentration of A. Now you have a Ka multiplied by Kb. Yes, put the value for here. Put the value for Ka here. Then it will be hydrogen ion concentration, acetate ions divided by concentration of acid. Then for the Kb, concentration of the acid, concentration of OH divided by like this one. So you can see this acid Ha and Ha cancelled, A and A cancelled here. So you will get concentration of hydrogen ions and concentration of OH ions is equal to Kw, and the Kw is always equal to 1 into 10 to the power minus 14 at 25 degrees Celsius. So this is same as before you done. Same as you before done like this one. Now if you want to go ahead for this, then what you have to do, multiply by this one. Multiply this equation. So this is the complete here. So when you reach here, then how we are going to write another one? So logs, multiply by log both. Logarithm of the Ka, Kb, log of Kw. So you will get logarithm of Ka and logarithm of Kb, log of Kw. After multiplying log, multiply by negative sign on both sides. So this will be a negative logarithm of Ka plus negative logarithm of Kb is equal to negative logarithm of Kw. So negative logarithm of K is equal to pKa, and this will be a pKb, and this will be a pKw, and this will be always equal to 14 at 25 degree Celsius. This is another formula you have. pKa plus pKb is equal to 14 at 25 degrees Celsius. So Ka is inverse of Kb. Kw is a constant, water dissociation constant. This is called Kb like this one. And if you write for the Kb, again the dissociation constant for water, this is the K inversely proportional like this one. Like this. Simple numericals are given, you have to solve yourself. pK for the acetic acid is a 4.76, calculate Kb value, pK for using this one. Use this formula and calculate in both cases. pK for the pyridine at 25 degrees centigrade is 8.25, calculate the value of pK same. You have to write here. Since I told you Kw is ionization constant for the water at a given temperature, it may be deduced that the Ka is inversely proportional to Kb. Already I have done here. Stronger the acid, weaker its conjugate base. Remember, hydrogen chloride, hydrochloric acid is a stronger acid. According to Bronsted-Lowry concept, react with water to give a hydronium ion and chloride ions. Hydrochloric acid has a conjugate base, chloride. Chloride is a conjugate base of the hydrochloric acid, so which is a weaker base. Acetic acid is a weak acid. According to the Bronsted-Lowry concept, react with water to give a hydronium ion and acetate ions. So students, acetate ions, acetate is a strong conjugate base of weak acetic acid. So here given here example, ammonia is a weaker base because its pK value is 4.76. Then diethylamine, which is a pK value is 3.02, pKb value. More the pK value, weaker the base. Less the pKb value, stronger the acid. So diethylamine has a 3.02 and pKb value for the ammonia is a 4.76. Therefore, conjugate acid of ammonia, because it's a weak base has a strong conjugate acid. So ammonia has a stronger conjugate acid than diethylamine. Similarly, for the already I told you conjugate base of weak acid. Acetic acid is a weak acid. Suppose we have water. pKa value is of 6, stronger base than that of conjugate base of stronger acid. Hydrochloric acid, the pK value is -7, very low, very strong acid. Thus the hydroxyl ion is a stronger base than chloride ions. So I told you acetic acid has a weak acid and acetate conjugate base is very strong here. So dear students, we can see here so this numerical I want to solve for you here. If you remember the previous numerical, same as this, what is the percentage ionization of acetic acid? Percentage of ionization of acetic acid of 0.0 molar solution has been dissolved per decimeter cube. Ka value is given and hint is given for the same you done before this. This numerical acid. So here is the acetic acid. CH3COOH. It gives hydrogen ions and acetate ions, and you have here the concentration is 1.1. You have a 0.1 concentration here. So initial concentration is a 0.1 m. Here 0 and here is going to be 0. So equilibrium concentration same. Equilibrium concentration is a 0.1 minus x, and this will be x and this will be a x, and you have a value of Ka, concentration of the hydrogen ions, concentration of acetate ions divided by concentration of acetic acid. So Ka value is given. Value of Ka is 1.8 into 10 raised to power minus 5, and concentration of the hydrogen ion is x and acetate is x square, divided by the 0.1 minus x. I told you this x will be smaller than 1.1, that's why it is going to be ignored. That's why 0.1 is x square, and 1.8 into 10 raised to power minus 5 x square divided by 0.1. So if you are going to solve this, so 1.8 into 10 raised to power minus 5, this will be multiplied by 0.1 and is equal to x square. If you solve this, if you are going to solve this one, then you will get for the value of Ka is concentration of ionized acid. So concentration of ionized acid, what will be the value? Suppose you will get this y after calculating this. Multiply by 0.1 this and x square, taking the under root for this, you will get the ionized acid. This suppose this is y, and percentage of ionization has formed. Concentration of ionized acid is y this, divided by original concentration is a 0.1 and multiply by 100. So you will be able to calculate the percentage of the ionization. The same numerical. This is the original concentration 0.1, initial concentration 0 and 0, and equilibrium concentration is going to be formed here. This is the equilibrium concentration. 0.1 minus x decreases, x increases here. So according to the law of mass action, concentration of the hydrogen ion, concentration of the acetic acid, Ka value, and put the value K is 1.8 minus 5 x square minus 0.1 minus x. X will be very small as compared to this one, so leave it. That's why x square divided by 0.1 and this cross multiply it. 1.8 10 raised to power minus 5 multiplied by 0.1. What is the value? X square. Take under root. You will get the value of y. Suppose this is called concentrated of ionized acid. This is y here. Percentage for the concentration of ionized acid divided by original concentration is 0.1 multiplied by 100. So you will get the answer that is 1.3. Students, we finish here. So inshallah, in the next we will start buffer solutions. Their applications, buffer solutions and their application in the next topic. topic we inshallah start. So thank you very much. We complete here.